Hey everyone, it's Mr. Anderson again. Today we're getting together to talk about section 6.1.2 in our CPM ebook. We've got a couple of goals today, and the main goal is to talk about something called the residual. It's what you see here at the top of that 6.1.2 lesson. A residual, don't even sweat it, just a fancy name for an error. And in order to introduce a residual, we're going to back up to an idea from 6.1.1. our last lesson. So if you haven't seen that one yet, folks, go ahead, watch that first, and then come back and tackle this. All right? A residual, as it's defined here, is the difference between what actually occurred and what was predicted by our best fit model. So we're going to look at a prediction. We're going to figure out how it differs or deviates from actual factual data. And we're going to call that a residual. And like I said, that's a fancy name for an error. Okay? And we start with the frame in problem 610. It says, Battle Creek Cereal is trying a variety of packaging sizes for their Crispy Puff cereal. Below is a list of 6 current packages. So you can look here. You can see in the independent variable column, the X column, we have packaging, cardboard, and square inches. In the Y, or dependent variable column, we have the net weight of the cereal, right? Makes sense there's probably a relationship. The more material we use for packaging, it could mean the more weight or more volume we can fit inside of that package, right? It says, write a few sentences to the executives of Battle Creek Cereal that describe the association and give the equation the executives can use to predict. It's going to be that line of best fit. The net weight of cereal based on the amount of cardboard used for the package. Tell the executives how much cereal the new experimental green package uses, that is 260 square inches of cardboard. Okay, so check this out. We're going to want to go ahead and do all this stuff for the executives, summarize what the data is saying. This is going to be really tough to do without seeing the data. So here's what I would go ahead and do. I would start by logging on to my Desmos machine, opening up Desmos, and I would go back and forth, and I'd click, and I'd add a table, and I'd start by typing in data. 34, the first package was 34, and it 34 square inches, my bad, of cardboard, and it held 21 grams of cereal. And then we had 150 square inches that held 198 grams, and so on and so forth. And you can see that I've got this thing set up. Now, I adjusted my window ahead of time, but I have a model starting to unfold as I'm typing in the data, and the data are showing me that, yeah, it's a pretty good, oops, I've got this one doubled up. Let me get rid of that, sorry. Okay, this should be 471 and 1020. Okay, and I've got a pretty good model starting to emerge here, and what I'm seeing here is a positive trend. It is pretty strong, but I see a little belly in there, a little curve. So a linear model is maybe not the best model. This is where I took all that data from. And you can see that I've got the model copied onto our notes, and if you're not sure what I mean when I say it's got a slight little belly, the curve kind of exists somewhere in there, and kind of right through here we see that curvy piece start to emerge. It doesn't mean we can't use a linear model for approximation. It just means we may want to have that in mind when putting together our description for the executive. So the first step toward any sort of creation for a model is to graph it and to see. Now, the next step after we're done with that is going to be to draw that line of fit. And the line of fit should follow the trend of our data. I already said it was positive. So that means our line of fit is going to increase from left to right. Okay. The other thing is we kind of want it to split our data in half. So here's kind of what I'm thinking. I'm going to kind of draw a line. Whoops, I got to have the pen selected. Kind of draw that line, and it's going to be doing something kind of like so. Okay. Now that's not perfect, and I'm going to actually try that again. Draw that line one more time. right, that looks pretty gosh darn good. It looks like we kind of go right through one point there, and I've got kind of three below. Maybe you could even argue that I'm going through that point as well, and then I've got 2 below. And if you were to do this on your own, you might even see, Anderson, my equation doesn't match yours, and that would be 100% fine. Okay, but 2 things that we really want to take away from this, and those are going to be slope and intercept. And the slope and intercept, I put in blanks in this y equals mx plus b form or slope and intercept model, and you can write these in kind of from the graph and from predictions. And here's kind of what I would say. I would argue that my intercept is right here, and I'm counting by 25s. Okay, I'm counting by 25s on my graph, so that is going to be negative 150, right? Because here's negative 100, negative 125, negative 150. There's my y-intercept, so I'll write that in right now, and I'll just put this in as minus 150. And now, let me get rid of that blank. The slope might be slightly harder, but still not impossible. I see that I've got a very, very nice point right there. And where can I find another really, really nice point? Gosh, I find it right there. And I'm counting by 25s on my graph, meaning I count up 25, I count over 25, I count up 25, over 25. These are equal units. So I can just treat this like a normal slope triangle, and I can just count the grids. So how many am I counting up, and how many I'm counting over? This is actually going to be pretty easy to answer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 1, 2, 3, 4, 5. So my slope is going to be 12 over 5. Now, some of you guys know already this is going to be for the purposes of prediction. So maybe you want to take that 12 over 5 and convert it into, take 12 divided by 5, 2.4x minus 1. 50. Okay, so there we go. We've got a good model that's going to allow us to do some predicting, and then they give me a prompt here, and I'm going to take this prompt and I'm going to run with it. Tell the executives how much cereal the new experimental green packaging uses. That is 260 square inches of cardboard. Okay, all right, and so I can go back to my model because that is my x. X is my input there. The amount of packaging, I can say, well, my expectation is that will hold this much material. I'm sorry, this many grams. Okay, and here's where I've got to use probably just a kind of real quick calculator. Follow my order of clear that off. Follow my order of operations. 2.4 times 260. Hit enter. And then I subtract the 150, and it looks to me like this is going to be 474. Now, do yourselves a favor. Write this up. Write it in a sentence. I would write to the executives that I expect this to hold 474 grams worth of cereal. Okay? Let's keep on keeping on, and let's talk about our big ticket item today, and that is this residual. The residual, we've got a formula for here, and the residual formula is actual minus predicted. Worth writing down, because what we're going to do is we're going to find an actual piece of data, we're going to calculate a predicted piece of data, and then we're going to go ahead and subtract the two. Okay? The 260 square inch box from the problem 610 will hold 355 grams of cereal. Your task is to figure out how we can calculate this residual distance on the scatter plot. So here's kind of what we're thinking, right? I'm going to go back up to here, and I'm going to get rid of my slope triangle. All right, and the 260 gram box is kind of, right in here. And I said I was going by 25, so it's going to be somewhere kind of right in there. Okay, and one of the ways we could do that is if this was graphed on here, I could just measure the distance from the line. The problem is I can't do that because I didn't have that information when I made that scatter plot. Well, that's not the end of the world for me because I can use some straight evaluation. Okay? The residual for this measurement Residual, I gotta make sure I'm spelling it right, is going to be the actual amount. Now they give that to me here. Actually hold 355 grams. Okay. 55. Okay. But then we're going to subtract the predicted. Now, I don't need to reinvent the wheel because my predicted amount, and hopefully you guys wrote a sentence on this, is 474 grams. Okay? I can't do this in my head. I've got to rely on the calculator. I could work it out, but it makes sense to just do this and come up with negative 119. Now, before you balk at negative 119 and say, holy cow, something must be wrong, it is okay for residuals to be negative. And what that means is that our residual predicted that this box would hold 119 grams more than the actual amount, or the actual amount was 119 under the prediction. And what we'd see if we went to graph this is we'd see, and I'll do this in red so it stands out, is we'd see on the 260 kind of benchmark here, we'd see a marker right here. What did they say? I got to go back and look. 355, sorry about that. We'd see right around here at 355, and we are calculating this distance right here to be about 119. That's how far off we are, and again showing that our prediction was over the residual value. Okay, one more thing we're going to look at real quick here, folks. All right, we're going to look at one more residual, and this time it is going to be for the 471 square inch box. We're going to mark it up on our scatter plot, and we're going to be sure to include the unit. So I'm going to do this all at once. Well, the residual, one more time, is going to be the actual minus the predicted. Okay, well, the actual is something I got to look up. Predicted, sorry about that, got to spell that correct. The actual is something I can look up. They tell me it is the 471 square inch box, and that is a 1,020 gram container. Well, great. Now what I need to do is I need to figure out my predicted value. My predicted value isn't too bad, and I'm going to do this down over here in blue. Okay, and for my predicted value, I'm going to use the equation that we came up with in 610, and that's this thing right here, 2.4 times x minus 150. All right, y equals 2.4 times x minus 150. Now, I didn't write x in there because I'm going to put the amount of material we have in there. All right, and this is going to allow me to make that prediction. So 2.4 times 471, I hit enter, I subtract 150, and then I get 980. That means that we predict that this will hold 980 grams of cereal. Now, do we know that to be true? No. That's what we've got the residual for. The residual is going to, 980.4, I'm sorry. The residual is going to help us calculate that error. So I go ahead and I subtract that value from 10, 20, or 1,020, and I get positive 39.6. Okay, ladies and gentlemen, positive 39.6, it said be sure to include the unit, grams. That means we've got a residual here that is 39.6 grams. And that for us, because our residual is positive, means our prediction was 39.6 grams under the actual value. Or another way we could say that is our actual value was 39.6 grams over our prediction. Okay? Ideally, whenever it comes to anything like this, we want those errors to be as small as possible. So smaller residuals like this one in 6-12 are better than larger residuals like this one in 6-11. Okay? But ideally, we want to know what the sign means. We want to know all about the size of the residual, and we want to be able to describe that well. Okay, last thing, number 6-13. I'm not going to have a ton of time to describe this, so I want you to try to wrap your brains around this quickly. The store wants to offer a supersized 600 square inch box. Is that a good idea? Well, Ask yourself this question, ladies and gentlemen. Do we have any data that suggests here it might be a good idea to make a prediction that large? We don't. That idea is called an extrapolation, and we don't do that for that reason. Folks, a little bit of review preview for you. Give these things a shot. Let us know what kind of questions you have. Thanks for watching. Have a